my YouTube channel. So for today, we are going to discuss about our new topic, which is stability of complex ions and chelate effect. In this topic, we have three parts, and this is the part 1, where we will discuss about the stability of complex ion. Okay, so here we have a formation of complex ion Ml from a metal M and also a ligand L in solvent that will become a solution. Okay, can be represented below. Okay, here we mix a metal and also ligand in the solvent, for example distilled water. Okay, so what happened here, it will form a complex ion solution. Okay, so in this reaction, okay, the metal and also ligand will form a complex ion Ml. Okay, so in this case, the stepwise constant, the K1, this is the constant, alright, for this reaction will be the concentration of the product divided by concentration of the reactants. Okay, so in this case, we have concentration of M and also concentration times concentration of L. Okay, so we add on another ligand, or 1 mole of ligand. So what happened here, this Ml will interact or will react with a ligand to form as Ml2. So what happened here, this is the second stepwise and we have a constant where we call it as K2. So the stepwise constant for this K2 is the concentration of the product. Here is the concentration of Ml2 divided by or over concentration of Ml plus concentration of L. Okay, so in this K1 and also K2, we have two ligands. Okay, and it will be going on until they form or until this complex ion is stable. Alright, so here, okay, the general formula or the general stepwise constant for the overall is Ml n minus 1, where n is actually the maximum coordination number of the metal ion, and for the ligand L plus with L, and then it will form as MLN, and the stepwise constant here is Kn equals to concentration of MLN divided by concentration of the reactants here, MLN minus 1, and also concentration of the ligand. Okay, so another way of expressing the equilibrium relation is where we have, other than the stepwise constant, we have also the overall formation constant. Okay, so for the overall formation constant, the formula here is the beta n equals to the K1 times K2 times K3 until at the maximum ligands that we have in that reaction, which is the Kn. Okay, so here, okay, what happened here, the magnitude of this overall formation constant is actually proportional to the stability of the complex form, where we have another formula, which is the log beta n. Okay, this is the overall, okay, equals to log K1 plus log K2 plus log K3 until log Kn. Alright, so other than that, okay, here this is an example. Okay, the stepwise constant or stepwise formation of cadmium 2+ ion with the ligand here we have ammonia, or we call it as amine. Okay, AMMINE. Alright, so what happened here, this cadmium is actually reacted with one NH3 ligand here, amine, to form as here, okay, this is the cadmium 2 compound where the K, the stepwise constant here is the 10 to the power of 2.65. Okay, then what happened in the K2, okay, the step number 2, this complex ion, okay, react with the NH3, and we are going to have the K2 until the most stable formation of this cadmium 2 plus with the ammonia here is the K4. Okay, this is the stepwise number 4, and the total for the K1, K2, K3 and also K4 is where we have the beta 4, okay, equals to 10 to the power of 7.12. Okay, so what happened here, okay, as the ligand, which is NH3, is added to the solution of metal ions. So here, let's say we have a beaker of metal in a solution. So this is the cadmium 2 plus, okay, aqueous in a solution. Okay, we add on ligand. Alright, here we have the NH3. Okay, so when we add on the ligand, okay, to the solution of the metal ion of this cadmium, Ml first forms. Okay, Ml, this is the Ml. Alright, okay, first forms more predominantly than any other complex in the series. So this is and then we add on, as the addition ligands is continued, we add on more of ligand. Okay, this Ml2, okay, this is the Ml2, okay, concentration rises rapidly while the concentration of the Ml drops. Okay, and then we add on again the ligand, so the Ml3 becomes dominant. So what happened to the Ml and Ml2? They become unimportant, and until, okay, the highest complex, okay, in this case we have Ml4, alright, metal with a 4 ligand, okay, is formed to the nearly complete exclusion of all others at very high ligand concentration. So at the final here, we managed to get, alright, this is the cadmium. I think the geometry here is tetrahedral, NH3 with a 4 NH3, 4 NH3 with the charge of 2 plus. Okay, alright. So this is another example, okay, of zinc complex ion, where we have a zinc 2 plus is actually reacted with a 4 NH3 or 4 ammonia to form tetraamine zinc 2. Okay, so for the stepwise for the overall of this is the Kf, okay, where we have the concentration of the product. Okay, so this is the concentration of product divided by concentration of the reactant. So we have two reactants here, zinc 2 plus. So we don't have any concentration here, okay, so this is only 1, okay, so 1, and then times concentration of 4 ammonia and H3, and then to the power of 4, okay, because we have 4 mole of ammonia and 1 mole of zinc 2 plus. Okay, so the value for the Kf here is given, okay, to us as 4.1 times 10 to the power of 8. Okay, so here what happened? Okay, displacement is a stepwise from the hydrated ion. Okay, so we have a step 1, alright. So this is the original, okay, complex ion, alright. When we add on the ligand, okay, so as you know, NH3 is much more stronger than H2O, water. Okay, So what happened here, this NH3 or ammonia here will replace one H2O from this 4H2O. So it will become zinc H2O3 with the additional of NH3 2 plus, and also it removes one H2O here. Okay, so this is where we have a displacement. Alright, and for the K1 is is the product divided by the concentration of the reactant. Okay, in this case, as you know, H2O is equal to 1. So you do not need to write down the H2O. Okay, alright, so it is a constant. Okay, 1. So if you times with anything with 1, you will still get the same number. Alright, so for the overall, okay, this is the K1 is actually equal to the B1 beta 1 with the value of 3.9 times 10 to the power of 2. Okay, so let's say we have another displacement with an additional of NH3. So this 2, okay, this 3 H2O, alright, and then we have one NH3 here, ammonia here. So this one will start to displace one of the H2O. So it will become zinc H2O2 and H3 2 because we have additional of this one and also this one. Okay, and removal of one water. Alright, so this is the K2, and the value or the B2 here, okay, is this is the K2, okay, the value of K2 2.1 times 10 to the power of 2. So if we combine this step 2 and also step 3, okay, it is actually between the K1 times the K2. Alright, so for the K2 here, for the K1 times K2, okay, what happened here, you can okay, so let's write the K2. Okay, so K1 and also alright, K2. So this K1 times K2, so you need to write down the this is the K1. Alright, so you need to times the K1 and also the K2. Okay, and then if you have, okay, or if you combine this K1 and K2, you will get this beta 2, okay, equals to beta 2 total, okay, overall formation. So you will get this constant, okay, the concentration of product divided by concentration of reactants. Okay, so in this case we have 2 concentration of NH3, so this is where we have the NH3 to the power of 2. Okay, and the value, okay, 8.2 times 10 to the power of 4. Alright, because we are given with the K1 value and also K2 values. Okay, K1 and also K2 values. Alright, so this is another example. Okay, all the values of the stepwise constant and also overall formation, so you do not need to remember everything. Okay, so if you look at this, okay, alright, in this table 25.6, what happened here, we have 3 types of ligands. Okay, we have a monodentate, and also we have a 2 ethylene diamine and also EDTA as a bidentate and also polydentate ligands. Alright, so if you look at the stepwise overall formation, alright, if you compare, okay, if you compare the monodentate with bidentate and also polydentate and bidentate, they have higher stepwise formation constant. Okay, so for example, in this case, 10 to the power of 10, 10 to the power of 7, and also 10 to the power of 18, 10 to the power of 9, and so on. And the overall here, okay, they have a larger values, okay, compared to the monodentate. Why this is happen? Because the EN, ethylene diamine, and also EDTA, other than they are polydentate, they have higher stability, okay, if we compare with the monodentate ligands. Alright, so I will explain to you a few factors that actually affect the stability of a complex ion. That's all for the part 1, stability of complex ion. So I hope you guys enjoy this video, and please like, comment, and also subscribe to my YouTube channel. So I'll see you guys in part 2. Bye.